This is video 11 for Computer Science 1124. Here's where we are in the grand scheme of things. We've already looked at low level. That was the binary stuff, bits and bytes, zeros and ones, all that. We have looked at mid-level. It's Python programming. Your project 2, project 1 was low level, project 2 is mid-level. Project 3 was high level. Object-oriented programming, when we start working with components and assembling components rather than writing everything from scratch so that we can get much bigger projects off the ground. The missing piece, if you go way back and review your notes at the beginning of the semester, the missing piece is theory. Theory, we can analyze programs and analyze code without actually writing the code. If we have a stepwise plan that we could look at and see whether or not that's going to work well, what the theory tries to answer is it even possible to write a computer program to do that? Of course, that's a big theoretical question. Another one is, if we do have a way that we're going to go about it, even though we might not have written it yet, we might want to analyze, well, how good is this going to be? Is this going to do really well if the number of items that we're trying to work with goes from 10 to 10 million? Or is it going to get just excruciatingly slow and therefore it's not even practical anymore? So the theoretical part is the missing piece of our overview of computer science for the entire semester. So how about we talk about theory for a little bit? Algorithm. A-L-G-O-R-I-T-H-M. The idea of an algorithm is central to computer science theory. There is a whole branch of theory called algorithm analysis, and that's what we're going to try to get just an idea of what's involved in that. An algorithm itself, a working definition, it's a stepwise sequence of instructions to solve a problem. Now, that is a working definition, but just about every word there doesn't have a lot of different acceptable replacements. Stepwise, it needs to be something that we can do one foot in front of the other. Very literally, take steps to solve the problem we're trying to solve. It's got to be a sequence. I could not rip out sequence and put in set, because set implies it doesn't really matter what order you do it. Instructions, they've got to be direct and tell us exactly what we need to do. And we've got to have a goal in mind. We've got to have a problem to solve. And it could be any sort of problem. Maybe my problem is I ran out of cookies. I can solve that problem by following a recipe. And ideally, for me, it's going to be a recipe where they even number the steps, 1, 2, 3, 4, 5. And it is a sequence. If you do them in the wrong order, you're not going to get cookies like you want. If you don't crack your eggs into a bowl and beat them slightly before you add it to the dry ingredients, then you're going to get a lot of shells in your cookies and you're not going to be happy with the result that you get. So that's not so good. Closer to computer science, your project 2. That is a realization of an algorithm. Solves a problem. Oh no, I don't know what my grade is in my class. So you set up a stepwise sequence that reads in all the grades that you've made and so forth and calculates averages, prints it all out, and boom, problem solved. We're going to get kind of generic and also a little more involved all at the same time. Without even filling up the whole board, I'm going to erase this because I know I'm going to use up the whole board with what's coming next. Our problem that we want to solve is this. Oh no! My list is out of order. That's a problem. I want my list to be in order. So what I'm going to try to do is develop an algorithm that will put my list in order. Here's an example. And you might think, well, why don't I just go down and write a solution? We're going to work our way up to a solution. We're going to start with a problem and just kind of go through it and see if we can figure out what it's going to do to, what it's going to take to fix it. For example, let's say these are my numbers. I've got numbers in my list: 9, 12, 3, 7, 10. And yeah, that's scrambled. That's out of order. And let's say we want to go for increasing order. It's going to be a similar algorithm to put them into decreasing order. But let's say we want to put them into increasing order. Let's see. Well, I can just eyeball that. That's going to be what? 3, 7, 9, 10, 12. Problem solved. That's not an algorithm. That's not a stepwise sequence. And that does not take into consideration the poor computer that is not quite as smart as we are by being able to just take a glance and say, okay, this is what they should be when they're in order. The computer, bless its heart, has to work under constraints. Constraint. Constraint just means there are some externally imposed rules that we're going to have to operate under. Here's a pretty important one with a computer. If you go back and review our if statements and our while statements and so on that have conditions in them, they can compare at most two things at a time. Is this number greater than the other one? Is that number greater than 0? They're always comparing two quantities. So a very important constraint for us to try to put this in order is to realize the computer can only see two numbers at a time. So you know what? Let's only ask it to do that. Mr. or Ms. Computer, what about those two numbers? Are those in order or are they out of order? Well, if we're going for increasing order, those are out of order. So I'm just going to mark through them, and this is sort of like a very loose variable trace here. So I swap it. The 9 will be first and then the 12. I hope it's clear what happened there. I just marked out those values. This is stored in a list. So there, a big list variable, and I've compared two numbers and they were out of order, so I swapped them. That wasn't too bad. Let's move on and shift and look at the next pair. What about 12 and 3? Computer, are those in order? Computer says, no, those are not in order. So we tell the computer to swap them. Where are all the steps? Where are all the numbers? Well, I'm getting there. Be patient. What you've got to do when you're developing an algorithm is observing the constraints, go through and do a solution by hand. And the way I describe it is, to develop your algorithm, you do a few examples like that and kind of look over your own shoulder. How am I doing that? And then see if you can use your vast expertise in Python, the toolbox of all the stuff we've looked at in Python so far this semester, and communicate to the computer how to do what you were doing yourself. And I'm never going to get these sorted if I keep stopping and talking about stuff. So let's say we move to the next two numbers and see if those two are in order. And you know what? Those aren't in order either. So we've got to swap the 12 and the 7. 7 there and 12 there. And then we've only got one pair of numbers left. The 12 and the 10, those are not even in order. So I swap those. Now, I'll bring all these down here. It's kind of a mess right now, but in the list right now, what I will have is 9, 3, 7, 10, and 12. I'll put a dotted line. That's the end of going through and look at all the pairs, and as if by magic, the list is not in order. So I guess that wasn't very magical. Are we done? No. Done. That's an easy question to answer. No, the list is not in order. So what could we do observing the constraint and only look at two numbers? Or we could go through again. Go through again. See if it makes it any improvement. Successive approximations. We'll sneak up on it and see if we can do it by just making it better and better at each step. Let's see. 3 and 9, those are not in order right off the bat. We got to swap two numbers. I'll put an arrow to show we're swapping. 3, 9. What about 9 and 7? No. Swap. 7, 9. What about 9, 10? Check. Finally, we found one we could leave alone. And 10 and 12, check. Those are also okay. So if I bring those down, I now have 3, 7, 9, 10, 12. Now, as if by magic. Are we done? Well, again, we're using our brains and the computer doesn't have our brain. Not yet. Not until the future. Are we done? We are. But there's a problem. But the computer doesn't know it. But the computer doesn't know. Why doesn't the computer know they're in order? Well, it can't stand back the way we can and just observe and look through it and say, you know what? 3, 7, 9, 10, 12, that's in order. So we have to come up with another way to let the computer know. Here's how the computer is going to know. The computer is going to use the mathematical rule of transitivity. If you have taken a math class where that was discussed, here's the rule of transitivity. We start and we'll look at the first pair again. You know what? That's in order. We don't have to swap this time. Check. Then move on. 7 and 9, are those okay? Yep, those are okay. We didn't have to swap them, so they're in order. 10 and 9, I got that backwards. They were in order, so we didn't have to swap them. Excuse me there. 9 and 10, those are in order, don't have to swap them. 10 and 12, those are in order, don't have to swap them. Check, 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 check. And I'll copy them down again just for old time's sake. 3, 7, 9, 10, 12. Done. Well, we were done before. Yes. But just as important as being done now, and the computer knows it. We're attributing artificial intelligence here. How does the computer know it? Well, if they were not in order, as we're going through this list from front to back, looking at each pair of numbers, the computer would have detected, you know what, that pair's out of order, I've got to swap those. And whenever it finds a pair that it has to swap, there's a possibility there are going to be others it has to swap. So the computer, with our algorithm, is just going to have to assume that if any pair is out of order, there's still the possibility that there's disorder elsewhere in the list. How will it ever know that the list is in order? If it can get through the whole thing, a clean pass all the way through from front to back without having to swap any pair. And that's where the transitivity rule comes in. Transitivity in math says if the first number is less than the second number is less than the third is less than the fourth, yada, 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 and I can say that all the way down, then the entire list must be in order. The entire list is in order if no individual pair is out of order. So there is where we get to stop our algorithm. That's how we'll know we've solved the problem, when we get to the point that we can go through the whole list and nobody has to get swapped. Now, memorize that. Make a visual image of that. Or perhaps better yet, you might want to write that down so you could refer back to it, because I'll be referring back to it. I've used up the whole board, so I've got no more space. You'll sometimes hear that referred to as a ghost trace of an algorithm. It was almost as if an algorithm existed and we were tracing it without even knowing what the algorithm was. So now we go backwards. We reverse engineer from what we just did, looking over our own shoulder, and see if we can formulate that as steps. So here will be my first stab at an algorithm. It's not officially an algorithm until you write it down in very clear, concise sequence of steps. That's not exactly what this is going to be. This is just going to be a description of what we did. Go through, abbreviated through, list from front to back. Well, we did that, but that's not even a single step all by itself. We did go through the list from front to back. What were we doing when we did that? Go through the list from front to back, comma, swapping pairs of numbers that are out of order. Okay, now let's stand back and see what we got. Go through the list from front to back. Go through the list from front to back. We did that. As we were going through the list from front to back, every time we ran into a pair of numbers that was out of order, we stopped right there and swapped them. So is that our algorithm? Go through the list from front to back, swapping pairs of numbers that are out of order. Well, no. If you copied down what I had on the whiteboard last time, that only gets us down to the first dotted line. That's one time through the array, also known as one iteration. One time through the complete list is one iteration, but one time through the complete list is not necessarily going to do it. In the general case, it will not do it. So I need another comma, and I need to keep going with my non-stepwise algorithm. Go through the list from front to back, swapping pairs of numbers that are out of order over and over. I had to do it over and over. And when did I stop? When did I stop? And so that the computer knew, yes, in fact, that list must be in order now. Over and over until no swaps occur. Until I can make a clean pass, front to back, without having to swap any numbers. There's no way the computer will know. There's no way my program will be able to detect that this list is now in order. Now, again, this is not an algorithm. It's the first stab at it. It's the first attempt to verbalize what we were just doing by hand with that specific example. We go through the list from front to back, swapping each pair of numbers that we run into that's out of order. And then the over and over is going through the list over and over. So this is kind of upside down. We will go through the list over and over until no swaps occur. So if we can get through the entire list without having to swap anything, that's going to mean that our list is in order. Now then, let me show you how smart you are. You know what? You'll have to wait and find out how smart you are in the next video. This will be my starting point when we actually start to crank out an actual algorithm with numbered steps, for crying out loud, that we could turn into Python. But until that time, see you online.